Hello everyone. In this video, we'll be looking into a static timing analysis for setup with real clocks. So when we have built the tree, we have looked into zero skew. So we have to actually look what actually goes wrong when there is a positive skew or when there is a negative skew, or basically whenever there is a non-zero skew, what goes wrong. And when we said that, we have already mentioned that there is an impact on the setup timing analysis, or there is an impact on the whole timing analysis. So we need to actually look what can go wrong with the bad skew or with a non-zero skew value. So let's try to look into that. So we have been given certain specifications. Okay, so we have a single clock on the chip. We'll be assuming that we have a single clock on the chip. The frequency of the clock is 1 gigahertz, and let us denote it by f. And since the frequency is 1 gigahertz, let's say the clock period is capital T, which is 1 by f, which is 1 by 1 gigahertz. It's 1 nanosecond. So these are the specifications, or the basic clock level specifications that has been given to us. So let us try to build the figure and the diagram and the equations based on this specification. So let us try to do that first. So this is a basic timing path. You have a launch flop, you have a capture flop, and you have some data path in between, and this is the clock path. So the clock goes the launch flop and the capture flop, and since we have only a single clock, so there is a single clock which is present over here, and we have built a tree across this part. Okay, so this is this, and the theta is the combinational delay, or basically theta will be the delay from this point to this point, and eventually we will be extending the value of theta. We'll looking into that, how are we going to use the value of theta and what the value of theta should be. Okay, so in this case, in this scenario, when there is no clock buffers, or when there is no clock tree built, in that scenario the clock is basically nothing but a single wire, so it is kept as ideal. So in ideal clock, we assume that there is no clock tree built. So basically the time required for the clock to reach from this port to this point, and the time required for the clock to reach from this port to this point is equal to 0. We'll assume that for now, and then we'll move forward. So without the clock tree, when clocks are ideal, the requirement that comes from this particular timing path is that if this is your waveform, which is 0 to t is nothing but your 1 nanoseconds. So the requirement that comes is that the combinational delay theta should be less than your time period t. Basically should be less than your clock frequency, and clock frequency basically the inverse of the clock frequency, which is the clock period. So this is the requirement that is basically we want to satisfy, we want to justify that your clock period, that your data path delay, the data path delay, which means it starts from clock to q to the complete combinational delay till this particular point, including the wires that are present over here. So all this theta, all this delay, which is nothing but theta, should be less than your clock period t. If this particular scenario is being met, we say that the system is working at 1 gigahertz. So that is basically the requirement. Now in the presence of clock tree also, we will be coming up with some equations that will justify the saying that your system will still work at 1 gigahertz. So how do we do that? Let's try to first build the clock tree over here. So it will be something like this. So the clock which enters from this particular port first hits the first buffer over here, then at this point it diverges. From this point it goes to the launch flop through one buffer, and then goes to the capture flop through two buffers. So this is, let's say, this is a clock tree that we have been building in the previous videos, and we have just generalized the clock tree diagram over here with respect to the launch flop and the capture flop. So here we are actually showing the flops over here. In the previous videos where we have been looking only into the clock endpoints. So here we are actually looking into the flops. So what we'll be doing is, now based on now this is called as real clocks. So when we propagate the clocks from this point to this particular clock and to this particular clock endpoint, how does this particular equation changes? Let us try to look into that first. Okay, we have to come up with some equation that says that if that particular equation is being met, your system will work at 1 gigahertz. Basically, we have to finally conclude that this particular system has to work at 1 gigahertz. And what are those equations, what are those conditions in the presence of this particular clock tree? And eventually we will be tuning the clock tree in such a way and see what can go wrong. So let us first start with the basic equation. So now your theta will not start from this point, but it will start from the clock point. Okay, so this is how we will be calculating the theta. So theta will be the combinational delay. Yes, it will be combinational delay, but in addition to the combinational delay, it will be the delay of this clock buffer and this clock buffer and the wires that are associated with this in this particular path. So theta will expand now. In this case, the theta will expand. So let's see how it expands. So theta will be the theta plus 1 plus 2. So if you see theta, if you calculate the theta, it from this point it will be 1 plus 2 plus theta. So this complete left hand side of the equation, this becomes the completely the left side of the equation, where theta is your combinational delay, which is this, and 1 plus 2 becomes your clock network delay, which is from this point to this point. So why clock network delay, or you can say it launch clock network delay? So when I say launch clock network delay, it basically says the time required for the clock to reach from the clock port to the launch flop clock endpoint. Okay, so that is what we call as launch clock delay. So theta is the combinational delay, the data path delay, and 1 plus 2 is the clock network delay, the one which I'm highlighting over here, or the one which I'm moving the cursor over here. So this is the launch clock network delay. Okay, that value should be less than some number. So it should be less than t plus 1 plus 3 plus 4. Now let us try to look into this 1 plus 3 plus 4. So initially t was this time period, basically because the clock was ideal in the previous case. So your capital T, the clock, the 1 nanosecond signal, or the rising edge at the 1 nanosecond will appear at 1 nanosecond. Now what will happen is the rising edge will appear not at 1 nanosecond, but it will appear after 1, 3, 4 delay. So it will be appearing after 1 plus 3 plus 4 clock delay, and this particular thing is called as the capture flop clock network delay. So it will be again capture clock network delay. And why it is called as capture clock network delay? Because the delays are being calculated, or the buffers are being calculated only in the capture path. So 1 plus 3 plus 4 comes in the capture path, 1 plus 2 comes in the launch path. The equation that becomes now is theta plus 1 plus 2 should be less than t plus 1 plus 3 plus 4. So let us try to see what is actually happening over here. So in the previous case, when the clock was ideal, when there were no buffers, your clock, the zeroth pulse of the clock will appear at zeroth pulse at the launch clock endpoint. But in presence of this clock buffers, in the presence of the buffers 1 and 2, the clock at this point will not appear at 0 time period, but it will appear after 1 plus 2. So the clock has to propagate through 1, through 2, and then hit this particular endpoint. Hence the rising edge, this particular rising edge will appear after some delay, which is 1 plus 2. So that is called as the launch clock network delay. Okay, next, the clock, when this particular thing was ideal, when the clock network was ideal, the rising edge at the capital T at 1 nanosecond was appearing at capital T at after clock period T, which is at this point. But now, since we have the clock buffers over here, since we have a small amount of delay over here, the next edge, that is at T, it has to move through this complete network and then hit over here. So the time period T will now not appear at time period T, or basically the next clock cycle will not come at 1 nanosecond, but it will come at 1 nanosecond plus 1 plus 3 plus 4 and plus the wire delays. So in this, that's why the equation is now a bit changing. It comes like theta plus 1 plus 2 is less than t plus 1 plus 3 plus 4. Let us try to generalize all this. So in this case, the 1 plus 2 are nothing but the are nothing but your launch flop clock network delay, and 1 plus 3 plus 4 are nothing but your capture clock network delay. Okay, so let us try to give them different names. Let us try to call this launch network delay as delta 1, and let us try to call the capture clock network delay as delta 2. So delta 1 becomes your this particular delay, basically 1 plus 2, and delta 2 becomes your 1 plus 3 plus 4. So from this particular equation, what is the thing that we can conclude? So basically we can conclude that this Q in this case is mod of delta 1 minus delta 2. We'll be coming into this Q equation in some time, but before that, this is the equation that becomes in that actually comes in the presence of a clock network, that is a clock tree that is being built from this point to the clock endpoints, and the tree that we have been building so far. So that particular equation, that particular buffer delays comes and sits over here. So this is where the timing gets impacted. And now what we'll do is we will try to look into a graphical format how this delta 1 and delta 2 comes into this picture, and this affects the waveform, and this affects the movement, or how it shifts the waveform. So since I'm already running out of time, so let us try to look into the shifting of the waveform, or try to understand the concept of the delta 1 and delta 2, or basically the concept of clock network delay in a graphical format in the next video. Let us try to cover all this in the next video. Thank you.